optimized or minimized. And the second one was for third one was for scheduling tasks or scheduling courses or choosing courses. Today we'll try to formalize such algorithms. We'll just develop a theory or theoretical understanding of such algorithms, and we'll give a mathematical foundation which explains functioning of greedy algorithm. Okay, so this following description of greedy algorithms, I've just taken it from Wikipedia. Maybe the slide rewordings. Okay, so yeah, in general, greedy algorithms, we can say there are 5 components. I mean, with full generality. So we have a solution space. Okay, so from which optimal solution needs to be computed. Okay, so which is true for almost all of optimization problems. Okay, so in the first example, that is storing files, the solution space is set of all orderings of files. In the second scheduling example, the solution space is set of all conflict-free schedules, which all of them need not be optimal. We need to pick the one which has a maximum number of classes or tasks in it. Okay, and in general, so we also need a selection function. So the imagination is the solution proceeds in is built in iterative fashion. So the selection function should determine which is the best candidate to be added. So for example, in the case of orderings of files, it was the next smallest file in the first case. In the second case, it was next smallest one, which has a smallest with respect to the ratio of file size and the frequency. Okay, and in the scheduling, it is the earliest finishing time, or class or task with the earliest finishing time. So that is a selection function. Feasibility function is essentially saying the candidate solution or the candidate that we are adding is feasible or not. That is, in the case of scheduling, it should be conflict free. In the first example, there is no feasibility. You need to store the file, so it's about an order. So every order is feasible. Okay, so their feasibility is not very non-trivial. Whereas in the scheduling example, feasibility function, you can imagine conflict freeness. Okay, so you need to ensure that there is conflict. So whatever task that you're adding to your bag is, it should not have any conflict with the already existing tasks in the bag. So usually these problems also come up with an objective function, which is basically the value that you need to optimize on. Okay, objective function in the first case is average access time. The second one is total access time given the frequencies. Third one is the size of the task or the number of tasks. That is objective function. Okay, so solution function would generally indicate if we have arrived at the solution or not. Okay, in the first example, there is no solution function as such. You need to just arrange the files. In the schedule example, solution function would say that, okay, no further. So if you take any other task which is not in your schedule, should be conflicting. So that is a solution function. Okay, so this is a generic description of greedy algorithm. We will not be doing this detailed analysis of greedy algorithm, in the sense that we will not look at these 5 components altogether. So instead, we'll take a generic kind of greedy algorithm and we'll try to analyze it, in the sense that, okay, what kinds of problems will have greedy algorithm, what kinds of problems will not have greedy algorithm. Okay, yeah. So, but these are the key features of greedy algorithm. Whenever you have greedy algorithm in mind, so this is how it should look like. But if you look at our examples, right, when you have so the first example, storing files, so there these are all hidden. Okay, so we didn't make it very explicit because it wasn't necessary to make them explicit. Okay, so one thing is this selection function, it was basically hidden by sorting. So once you sort the files, right, everything is done. But what actually is happening there, you're choosing the first files to be stored is the smallest size. the next one is the next smallest size, and so on. Okay, so the selection function was implicit there. Okay, once you, I mean, the easiest way to implement it is by just sorting them. Okay. So we'll discuss essential features of greedy algorithms or problems that admit greedy algorithms. Okay. So one of them is the.
Hello. Hello.
Yeah, yeah. Go ahead.
Yes, sir. I have a question. In the previous slide, can you explain the
Yeah.
solution
So the
function?
solution function basically says you have a solution or not. Okay. So in the case of conflict-free scheduling, right? Solution function would say every remaining task or all of the tasks which are not included in your schedule should be in conflict. That means it is a solution, right? Well, it's a maximal solution, but yeah, maximum. Well, the solution function is not simple to describe, but you have to say that okay, the schedule is maximum. When we say solution function, let's talk about maximal for now. Okay, so that means it's essentially says that okay, you have a solution or not. That's it. You have a feasible solution or not, because in general, greedy output need not be optimal solution. Yeah.
So, what's the difference between feasibility and solution function?
No, solution function. Okay, there is no difference as such. Yeah, that's true. I mean, in what I mentioned, yes, there is no difference. No. So feasibility function is different. Sorry, here the feasibility function is different. Yeah. So this solution function basically says it's well, it is not actually. So there is a difference. Okay. See here, feasibility function is whatever candidate you are going to add, is it feasible or not? Okay. Is that task, say for example, in the case of task, is that task conflict free with your existing schedule? Whereas solution function says, is your schedule not optimal? Is it maximal? That is, you cannot add anything further. That is all. So in the case of scheduling, it both the functionalities look the same, but they are not the same functions. Because one basically says, okay, given this task, can it be added to my existing schedule or not? This one says, none of the remaining tasks can be added to the schedule. Hence, it is, let's call it as maximal. Okay.
Can you give the example of the solution function in case of like storing the files on a tape?
There is no, yeah, storing files is an exception. There is no solution function, right? Because any ordering is a solution there.
Okay, sir. Thank you.
Yeah, so yeah, that's all. I mean, okay, technically you can say if you have stored all files or not. That's a solution function.
So it will be the optimal solution, not solution function.
See, optimal solution, no. See, the problem is, like I said, right, greedy algorithms need not be always correct. Okay, now, for example, correct. So optimal, deciding if the solution you have obtained optimal or not, that is not trivial. So usually you just take, if so you can imagine in this scheduling example, it is maximal. Okay. If your task was to minimize, you can say it as minimal. Okay, but it need not be the optimal always. In our examples, it happens to be optimal, because see, these functions should be doable in your algorithm, so you should be able to test it. So that there is no hard boundary on it. I mean, you can take as well solution function as checking if it is optimal or not, but then I mean, then you would have used that itself to build the solution, right? Why do you need greedy strategy? Because usually checking if something is optimal is a harder task. Okay. So for example, if you take, I hope you're familiar with the minimum spanning tree algorithms, right?
Yes, sir.
At least you must have heard of it. So given a spanning tree, to check if it is a minimum spanning tree, minimum weight or not, it's a non-trivial job, right? It's not easy. You may have to run the algorithm for computing minimum spanning tree and check if it matches, right? So that minimum condition, it's usually hard to check. It's not easy. So again, if somebody gives you a conflict scheduling, it's not easy to say tell outright that is it the optimal. You'll have to compute something which is optimal, right? So that way, we'll not be looking for optimal. We'll just look for, like Pranay said, right? Feasibility. But here, feasibility, we are also looking at maximality. That is, you cannot improve it further. That is all. Okay. Yeah.
So,
Like I said, yeah.
sir, in case of that scheduling classes, we will be going to have more than one solution function, right?
You have more than one solution function, but see, if somebody gives you a schedule, right, you cannot tell it is optimal or not. Well, now we know that sorted ordering is the optimal, but without that knowledge, you cannot tell it, right?
Yes, sir.
So their solution function does not make much of a difference as such. Okay, so I mean, like I said, I mean, this is a general or whatever full general description of a greedy algorithm. We will not be really nitpicking on all the specific function. We'll be actually looking at a very simplified version of it. I'll come to it very soon. Okay, very simplified skeleton. So this is something that all of you need to know. That's all. Okay, so there could be a problem where all of these 5 things are very specific. So I can't think of such an example. I mean, all of the examples that I have in mind are much more simpler than this. Okay. Okay, can I move ahead?
Sir, could you repeat that feasibility function?
Yeah, so feasibility is basically, it's like, so for example, in the scheduling, right? So when you pick a new task to be added to your schedule, is it conflict free or not? That is a feasibility function. That is, you are improving your solution by adding things which can, I mean, adding things from the candidate zone or a candidate set. When you add it, it should say, can you add it or not? Is it feasible or not?
Okay, sir.
Is that clear?
Okay, okay.
Yeah.
Hello.
Yes.
So can we say this in this way, like in course scheduling, feasibility we will check whether a particular course can be added or not to the schedule,
Yes.
but
Yes. Yes.
solution will ensure that there are no courses left such that they can be added.
That's all. It's maximal or not.
Okay.
You can imagine it that way. See, ideally it should have been maximum, but a maximum is not something easily testable. Okay, so that is why. So see, all these, I mean, particularly this solution and feasibility, they are kind of vague descriptions. Okay, generally, I mean, given a greedy algorithm, so only thing that I can think of which you can extract possibly everything is the minimum spanning tree. Okay, which we will be discussing soon. So where all characteristics can be extracted. Okay, so either prims or cruscals, you can extract the features. But otherwise, in general, it's not very easy to extract all the features. So we'll, in the next 2 slides, we'll discuss some essential features which are necessary for a greedy algorithm. Okay.
Okay, sir.
So the essential features, there are basically 2 essential features. One is greedy choice property, the other one is optimal substructure property. Okay. So, like I said, a greedy algorithm we can imagine as an iterative procedure, which I would say greedily pick the best possible locally, best possible candidate to be added and keeps on adding until no further addition is possible to your solution set. Okay, imagining solution is a set. Okay, so yeah, greedy choice is a best choice at the moment. Okay, so the only important thing is, so the choice made by the greedy algorithm or a greedy algorithm, it may depend on the choices made so far, but should not depend on future choices. Okay, it should not foresee, okay, I'm going to add this candidate later, so this is the right candidate now. Okay, so that is the crucial point. So any algorithm which iteratively builds solution such a way that, so locally it makes best choice at the moment, be it scheduling or be it storing files, but it should not bother about some choice to be made in the future. Okay. And also one more thing is, it should not revise the solution. There is no revisiting. So once you make the choice, that choice is going to be with you till the end. Your solution will have that element. Okay. So this is the property. The second one is the optimal substructure. Okay. So this is more implicit to the problem. So we say that a problem exhibits optimal substructure if an optimal solution to the problem contains optimal solution to the subproblems. Okay. The easiest thing is the following. So I mean, easiest way to demonstrate this is the following. Okay. So the first one, greedy choice. Let's take the scheduling example. Okay. So in the case of scheduling example, so greedy choice says, okay, you greedily pick the best possible task which can be scheduled with respect to the current schedule. That can be added to the current schedule. Okay, so what was a greedy choice there? So greedy was among the remaining tasks, choose the one which finishes earliest. That was a greedy choice. Okay, so when you say greedy, I mean there is some optimization, local optimization that you do there. Okay, so in the case of optimal substructures, so now whatever solution that you have built, so that solution will stay even if you drop some of the tasks. So for example, in the case of scheduling, right? So if you have a solution, so that is S. Okay, we used X, right? So X is your solution. Okay. Now, if I consider a problem instance by dropping some of the tasks, okay, say task 5, 7, 9 are dropped. Now, if I drop the corresponding tasks from X2, that is, if 5 occurs in X, then I drop 5, 7 occurs in X, drop 7, and so on. The corresponding will also be a solution for the new instance, that is a sub instance. Okay, so that is what this means. So when you consider sub problems, in this case, in the case of scheduling, sub problems are nothing but considering a subset of tasks or subset of classes. Okay, and then your schedule should also have solution to that. That is, by dropping the corresponding ones, you should also be getting solution. This is essentially true for scheduling. I'm not going to prove it. It's not very difficult to prove either. So these are the two properties we call as essential for greedy algorithms. So one is the greedy choice property, so which in the scheduling case, the best possible conflict-free task, I mean best possible task which can be added so that the schedule is still conflict-free. Okay. Okay, so these are the things that we need to keep in mind. We will not really discuss about this right away. So instead, I'm going to give a formalization. I'll just have a skeleton greedy algorithm, and then we'll try to build mathematical foundation when such greedy algorithms will work. That is, what kinds of problems it will work and what kinds of problems it will not work. Okay. Yeah. So at this level, is it clear what we mean? At least with the scheduling example, the storing files is kind of, I mean, it won't fit in all of this. I mean, it admits greedy algorithm, but it does not have, because you have to store everything, right? So that the solution is not a subset. Solution is just a permutation. Okay.
Sir,
Hello.
Yes. Yes.
Is it
One of
like
you. Yeah.
is it like divide and conquer?
No, this is not like divide and conquer, right? You're not dividing instance into some smaller sub-instances. See,
But here
optimal
we have,
structure, no, it's a property. It's a property, right? So if I have a solution, okay? Now, if I take an instance which is a subset of the original instance, that is a sub-problem. So this solution should also contain a solution for that. That's all it says. Okay.
does, like, even in divide and conquer we have this, right?
No, divide and conquer not necessary that you have this property. No.
Okay.
Divide and conquer also involves a way of combine. And so divide and conquer essentially says, okay, given an instance, you divide into sub-instances and solve them independently, and then have a kind of, I'll call it as merge function or a combination function which combines these two solutions. It does some processing of these two solutions to get a solution for the original problem. This does not say that. It says if you take any solution for any sub-instance, that is any subset of 1 to n, if you take those as the tasks, initial tasks, then if you drop the corresponding ones which you have dropped from the original thing, it will. So, for example, I'll give you a concrete example. Okay, so let's say my tasks are 1 to n, say 1 to 10. Okay, my solution x is 1, 4, 6, 7, 9. Okay, now my S is I'm changing it to, so 1, 3, 5, 6, 7, 8, 10. Okay, this is my instance now. So how many? 7 elements, right? Yeah. So now I consider x prime, which is a subset of x intersection s. What is that? 1, 6, 1, 6, 7. So the optimal substructure property says this is optimal solution for S. Now, X prime is an optimal solution. That's all it says. So that is solution for the original instance contains solutions for all sub-instances of the original instance. Okay, that is all it says. And it's a,
Okay.
if you look at it, it's a severe restriction. Okay, so this is a property of the problem. This is not property of your solution. It should be property of the problem. Okay. Yeah. That is essentially what it says. Like if you have a solution for an instance, if I take any sub-instance or sub-problem as we call it, okay, this from this solution itself you can obtain a solution for the sub-problem. When I say obtaining should be trivial. That is, you just drop out whatever you need to exclude. That is it. So in this case, we needed to exclude the task 4 was not present in the new instance. Task 9 was not present. So we need to just drop it. What else we had to drop? 5 was not present. Okay, 5 was not in the solution itself. So that is all we did. Okay. Yeah. Yeah, Shira, you had a question?
Sir, because optimal substructure exists, that's why greedy choices work, right?
Yes. So that is the essential feature of the problem for admitting greedy algorithm. Okay.
Okay, so then in that sense, optimal substructure is the only one property it should exhibit, right?
Not really. I mean, so the first one is also something essential. I mean, you need to have this greedy choice. You should be able to see if the greedy choice is something very difficult to compute, right? So if there is no greedy choice, it's difficult. So these two are essential features. Yeah. So yeah, like I said, I mean, these are very, very abstract terms. Okay. So in most of the algorithm textbooks, I think this is the explanation that you would have seen. Okay, so
so sir,
yeah.
Are we saying that if a problem exhibits these two properties, then we can have a greedy solution to that problem?
Yeah, so that is something I mean, it is true. I mean, as a statement, it is true. But for me, I mean, it's not a technically precise statement I can make. Okay, because I don't know how to prove it as such.
Okay.
Because Yeah, so when I say, I mean, see, none of these are formal for me. Okay, so I mean, our job is to do analysis of algorithms. So we want mathematically precise statements. Okay, so what I said was these two were some things that you would see in common algorithm textbooks. Okay, in the remainder of this lecture and the next lecture, I'm going to formalize this completely. I'm going to give a complete mathematical description of these. You don't have to use these terminologies at all. You give a complete mathematical formalization, which essentially implies these two things. Okay, greedy choice as well as optimal substructure. But if you show that the problem satisfies those conditions that we are going to state soon, then you know that there is a greedy algorithm. That's it. Okay. But
Yes.
many of the textbooks you have seen would say, okay, if the problem exhibits greedy choice property as well as optimal substructure, then it admits greedy algorithm. So what we are going to do is you are going to establish mathematical foundations so that we can prove this statement. Okay, so that is what. Right now, I'm not really stating it or proving. I'm just saying essential features of greedy algorithm or problem which exhibits greedy algorithm. Okay. So I'll just state one generic greedy algorithm. Okay, I'll not spend more than 2-3 minutes on this. Okay. So a generic greedy algorithm will look like this. Okay, so you have an initial solution, which in most of the cases it will be an empty set. Okay, and you have a choice space. So in our scheduling case, this is set of all tasks. Initial schedule is an empty schedule. Okay, so as long as schedule the current set of tasks which are not yet scheduled is not empty, so what you do is you make a greedy choice. So X be a greedy choice. So this greedy choice will depend on your problem. In the case of scheduling, it was conflict freeness. Okay, so that is it should not conflict with any of the tasks in I. Now you set I as I union X and you update S accordingly. In the case of scheduling, all tasks that conflict with X will be thrown out. Okay, and finally you output I. So these are the 3 steps you repeat until S is empty. Okay, so here, I mean, I've just moved away from my first slide where I gave 5 points, right? So we don't have that. So this is a simplistic greedy algorithm. Okay, so everything is hidden there. So when I say greedy choice, there is an objective function, there is a feasibility condition. So all of these are hidden there. Okay. So the purpose is simple. I mean, I just want to see a greedy algorithm as a process of building some set and outputting that set. Okay. So the process is the following. I should be having an iterative procedure, and so there is something which guides me how to choose. So we call that as greedy choice. Okay. And we should be updating the solution, but the only thing is we should not be going back. So that is when I include X, say X is task 10 in my schedule, I should not be going back on my words and revising my solution. No. Once I decide to choose 10, it stays in my solution. Okay, so that is the essential property of greedy. That's called greedy choice. Okay, once you make that choice, you are not going to leave that out. Okay, so now, so what are the things that we expect here, or what? I mean, I'll just give a typical scenario. Okay, so here, so the most important is the greedy choice. Okay, so when we have a greedy algorithm, so I don't know if you have heard of so many scenarios people use greedy algorithms. Okay, so for many of the problems, even in cases where the algorithms are not known to be optimal or known to be not optimal, in either cases people prefer greedy algorithm because they are simplicity. Okay, they're essentially very simple to implement. So this greedy choice usually should be very efficient. Okay, so you can say order n time. Ideally order 1 time will be good, or even order n square time. It should not be something which consumes exponential, but not 2 power n, etc. Okay. And similarly here, this is also usually very efficient. Similar to the previous one, order n or order n square. It depends on the problem, but not exponential. So these are not formal requirement. So whenever you want to design a greedy algorithm, when you want to fit your algorithm into this structure, so to call it a greedy algorithm, these are kind of features which are desirable. Okay, so if this is so this greedy choice itself is something like you are going over all possible solutions and then picking one. Okay, that's not going to be efficient. That's not why we want a greedy algorithm. Okay, so when I say greedy algorithm, so the greedy choice should be very simple. And similarly, the update should be very simple, should not be very difficult. So when I say simple, I don't have a mathematical definition of what is simple and what is complex. Similarly, so when you say greedy choice, I don't have a mathematical definition of efficient, but for our intuitive understanding, you should imagine that these are algorithms which run in say linear time or quadratic time or in polynomial time in general. Okay. Yeah. So any question? Is this clear? So the skeleton greedy algorithm or generic greedy algorithm. So we are going to talk about such greedy algorithms. So like I said, these are not issues we'll be bothering about now. Okay. So this is a generic guideline. So whenever you think about greedy algorithm, this is what desirable features are. In fact, all of the greedy algorithms that we analyze will satisfy these features. Okay. So this kind of efficiencies. So we are going to look at this structure, okay, and going to say what kinds of problems will admit. So that is when you output I, it's going to be an optimal solution always, no matter what your choices are. Okay. So yeah, so pause for a minute and think, how do you fit in the scheduling algorithm into this? That is the class scheduling, conflict-free scheduling. So only extra thing that you do is you need to have all classes or tasks which are in ascending order of their finishing time, right? Then this is essentially it. That's what it does, right? You choose a task which is conflict-free, add it, and then remove all tasks which are in conflict with the newly added task, and keep on doing it until you are not left with any task. Okay. Yeah. Any questions? Okay. So now I'll give an example where the greedy fails. Okay. So far we have seen, we have seen scheduling as well as storing files. And we also kind of know that minimum spanning tree it works. We'll be discussing it after 2 lectures or so. Let's consider the following problem. That is a matching, computing a maximum size matching. Okay. So here the input is an undirected graph. We say that a subset of edges is matching if for every pair of edges in the subset, they do not share any endpoint. Okay. So I'll give example with this graph. So let's consider this graph here with the 6 vertices. So let's consider a matching. Okay. So maybe with the green edges. Edge 1, 2, edge 3, 4, edge 5, 6. So M is 1, 2, 3, 4, 6, 5. Okay, so one thing, so I just write this as ordered pair, even for undirected graph, I mean, just for convenience. So these are unordered pairs, okay? So these are basically like sets. Now, so this is a matching. A non-matching would be, okay, so why is this a matching? So 1, 2 does not intersect any of these edges. 3, 4 does not intersect any of these edges. 6, 5 does not intersect, okay? So they are independent. So I mean, we call them as independent edges, that is, which do not share a common point. A non-matching is the following example. So let's say 1, 2, 1, 6, 5, 3. Yeah, so let's take this. Okay, so this is a non-matching because there are common vertices here. Okay, I mean common vertex. So one is common between the two edges. So when you have n edges, what is the maximum size of matching in that graph with sorry, n vertices? I mean maximum possible size. So each edge will consume two vertices, right? And no two edges can share an endpoint, that is, share a vertex. That means you can have at most n by 2 edges in any matching. Okay, so in other words, so here there are 6 vertices. So my set already has 3 edges. So this is maximum. This also happens to be maximum. Simply for that reason. Because I cannot have more than n by 2. If n is the number of vertices, I cannot have more than n by 2 edges in any matching. Okay, so that is it. So hence this has to be the maximum. Is it clear what is a matching? Those who haven't heard of it before? Okay, so now our problem is the following. We just want maximum cardinality matching. That is max. So given a graph, we want to compute or output maximum cardinality matching. Okay, so this is our maximum cardinality matching problem. So given an undirected graph as an input, we want to output a matching M such that size, that is number of edges in M, is the maximum. Okay. So let's look at a greedy algorithm for this. So how a greedy algorithm look like? So we're essentially taking the generic greedy algorithm and fitting into this matching scenario. Okay. So we initialize the matching with the empty set, and the candidates are basically set of all edges. So let's take S as E. Okay. So we'll repeat steps until S is non-empty, as long as S has at least an edge. So what is a greedy choice? This is the greedy choice. So choose an edge E such that E has no common vertex with any of the edges in M. That is our greedy choice. So the objective function or the feasibility condition there is basically there should be no common vertex with any of the edges in M. Okay, so you just add that to the matching, and now you have to do a processing of S. You have to remove all vertices which share an edge. Sorry, all edges that share a vertex with E. Okay, that is S prime is set of all edges. So I'm misusing this notation. I'm saying E prime is non-empty. That is, they share a common vertex. Okay, set S minus S prime. So at the end of this, when S is empty, you output M. That means you cannot add any further edges. Okay. So let's demonstrate. Is the algorithm clear to everybody? Okay, so I hope it is clear. So we'll demonstrate it with an example. Okay. So M was initially empty. Sorry. So now the greedy choice. So what would you choose? Any edge is fine, right? So the whole edge set is going to be my S. So S is E. Okay. So okay, suggest some edge. Because there is no differentiation between any of the edges right now, right? With respect to our algorithm. So pick something.
2, 4, sir.
Yeah, somebody? 2, 4.
2, 4.
2, 4. Yeah. So E is 2, 4. So I'm setting M as 2, 4. The edge 2, 4. And what should I remove? What are the edges that should be removed? All edges that are incident on 2 as well as 4. 2 and 4. Okay. That is, I remove. So let's mark it as red. Okay. Remove, 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 remove. Okay. So S is the remaining edges. 8, 1, 1, 6, 7, 6, 8, 7, 7, 5, 5, 3. Did I miss anything? That's it, right? Everything else is incident on either 2 or 4. Okay, so this is iteration 1. So of the remaining graph, what edge should we pick?
Sir, 8,
Give me
6
some
is
suggestion.
also there.
8, 6. 8, 6 is also there. I missed it. Okay, sorry. 8, 6. Anything else did I miss?
No, that much.
Okay. Yeah. So suggest an edge for iteration 2. Anything which is conflict free, right?
6, 7.
Sorry?
6, 7.
6, 7. Okay. So E is 6, 7. M is 2, 4, 6, 7. So what is S now? Quickly. So 6, 7. So let's mark in. So 6, all these edges are gone. 7, all these edges are gone. Okay. So now what are the edges? 1, 8, 5, 3. Is that right? So next will be, so this is iteration 2. Iteration 3, you pick any of the remaining edge. So 1, 8. M will be 2, 4, 6, 7, 1, 8. S will be 5, 3. This is iteration 3. Now iteration 4, E will be whatever is remaining. 5, 3. M is 2, 4, 6, 7, 1, 8, 5, 3. Okay. So is this maximum? The matching you got?
Yes.
Yes.
It is maximum, right? Because there are 8 vertices and we have already 4 edges. So n by 2. So it must be maximum. So can I say that the greedy algorithm works?
Hello.
Yes.
Sir, are we saying that M should be maximum possible in that graph? In the question?
Yes, of course. Yes, of course.
Okay. Okay.
It's a maximum possible edges that you can have in a matching in that graph. That's how it is, right? It's a subset of edges from the graph, right? So if you look at this,
So,
No, the maximum need not be n by 2 always, that I was thinking.
yeah, that is
Could
true.
be less than
See, in
that.
this case, we know that it was easy to say it is maximum or not. It could be that your graph does not have n by 2 matching of size n by 2. Yes, that is true.
Okay.
Yeah, in this case, it is n by 2. So once it is n by 2, we for sure know that it is maximum. That is all. Yeah. There is a question.
sir, here we at first chose E equals to 2, 4. That is why we got the maximum matching. But it did
Okay.
not always, because it depends on the first choice, no? I mean, and the subsequent choice we are making.
Yeah, that's a very good point. So any other thoughts? So is it Anuja? Are you Anuja?
Yes, sir.
Okay. So Anuja was saying it is because of the choices that we made we got this solution. She says greedy will not work always. What about others? What do you think? Is it because of the choices we made, or see here? Somebody suggested 2, 4. I just took 2, 4. Somebody suggested 6, 7. I took. Then there were only 1, 8 and 5, 3 were the only choices. So I took them. Okay. So we arrived at the solution. So then why can't we say that okay, now greedy works fine? We got the solution.
Sir, but actually the input was given by us now in every iteration. The algorithm did not take the input always.
The algorithm did not take. What do you mean by input? So input was given. I mean, input of course will be given by someone who runs the algorithm, right? So
no,
this graph is the input.
No, not like that, sir. Like for example, we took 2, 4 or 6, 7 or 1, 8. That decision was made
That's
by
not.
us.
That is not input. What you mean is the choice.
Yes, sir.
Choice was determined by us. That's what you're saying.
Yes, yes.
Yeah. So more precisely, see, there was no reason why we had to pick 2, 4, right? There is no differentiator. Any of the edges could have been chosen, right?
Sir, actually, in the previous examples of greedy and all, there is like a sorting kind of relation between the inputs. We actually know there is a relation between them, but here there is no relation actually between the edges.
Yeah,
The
but
choices.
that's not necessary, right? I mean, what I mean is, that's not really necessary as such. So why should there be a relation? So you're suspecting that okay, because there is no such relation, it may not work. Is that what your thought is?
Because any choice can fit in, right? There actually the best possible at that moment is fitting.
Okay.
So here any choice can fit in.
Yeah, that's a good suspicion. It's not because of that. Okay, so but yeah, it's a good suspicion. Okay. I mean, I'll come to that later. Yeah.
Can we just get to this by a small example? Like we have 4 vertices, 1, 2, 3, 4.
No, I'll come to that. I'll come to that. I'm just hearing from people. So yeah.
Okay. So in that example, we can say that directly based on the choice we make, whether it is greedy, like we say it is greedy, but even if it is greedy, based on the choice we make, the solution will depend on that.
Yeah, that is true. So even here, it should be possible, right? So even here, it should be possible to make such a choice. Let's see.
The choice we make may also be a guided choice, right? If number of vertices are going to be high, we may arrive at the algorithm with the lesser steps, possibly, but then it can be a guided choice or educated guess, kind of.
No, I didn't get what. No.
Say for example, if I take 6 is in this graph as the maximum, edges ending in, right? The next is possibly 4. If I choose 6, 4, and then do this exercise, we may arrive at a number of iterations, may possibly be less. I'm not saying it will be
So you're
less.
saying you may not get an optimal solution. That's what you're saying, right?
Yeah.
So let's see. I mean, it should be possible, I guess. So let's see. So okay, so let's make. So I just made 2 copies of it so that we can experiment. Okay, so we have a couple of minutes. Okay, quickly. Okay, so let me first make this as the first choice. Okay, so 6 4. So if I make 6 4, then what do I have? Okay, so the next choice I have to optimize again, right? So all of these interior edges are gone, right? Now, so next choice will be 1 2. Okay, sorry, yeah, it should be blue. Now what happens? So now these edges are gone. Okay, next choice will be 7 5. I still have. So can I go further? So with this choice, I have exhausted everything, right? All the edges are gone. Now nothing remaining. So all these edges are gone. Right? In fact, this one also. So with this choice, so I started with 6 4, then 1 2, and then 7 5. I ended up with the matching of size 3 instead of 4. And there are 2 vertices which are still unmatched. In our original solution, they were matched, right? So this is one way. So there could be other ways also. I'll just leave it to you to try out on this other, the other drawing of the same graph. Okay. So yeah, I mean here, well, I chose. So did the order really matter? I could have chosen 1 2 first, and then 6 4, then 7 5, or I could have chosen 7 5 first, and then 1 2, and then 6 4, right? Any of this would have led to the same. But instead, if I had chosen 3 4, I would have got an optimal solution in this case. Okay, so there is an ambiguity on the choice. Okay, so algorithm really cannot differentiate. This generic algorithm here cannot really differentiate. Okay, so all we say is, okay, you choose an edge which fits possibly. Now some of you can say, okay, maybe you didn't sort or you didn't order whether according to the degrees. Maybe you should order according to degrees. The least degree one should be the first, and so on. Okay. So I'm not going to refute each of individual claims. Okay. So what I'm going to say is, no matter really what you do. Okay. So no matter what choices, be it degree ordering or be it any other kinds of ordering of the edges, you are going to end up with a similar scenario. So only thing is a task of considering a counter example, that is a sequence which actually does not give you optimal matching, will be harder. Particularly with the degree ordering, it will be harder. Okay. So what we are going to do is we are going to give a definition, formal definition, which actually tells. Okay. So any algorithm which admits greedy algorithm should fit into this definition. So once that does, then that's essentially it. So we can show that matching will not fit into that definition. So hence it will not work, no matter what kind of greedy algorithm. You will have to revise the solution. There's no other way out. So I mean, what I mean is, any modified procedure you modify here to implement. So when I say modify here, with a reasonable time bound. You should not be doing an exponential computation there and then, okay, saying add this. That is not what I'm talking about. Okay. So a reasonable procedure, which basically does a local choice of addition of edge, essentially something which has no conflict with the current matching. So you're choosing an edge which has no conflict with the current matching. Among those, you might prioritize, maybe highest degree, lowest degree, whatever. okay, or highest average degree. So you can consider edges, endpoints, and take their degrees and take the average. Okay, so with the least average degree or most average degree, you can do any of that, but they are not going to work. Okay, so yeah. Okay, so just for your quick consumption, I'll go over this again, just so that it's in your head. I'll just give a formal definition of what are known as matroids. Okay. So here, what we are going to do is, so what are the solutions here? Mappings are basically subsets of edges, right? In the case of scheduling, what is a feasible solution? Set of all conflict-free schedules. Okay. So we are imposing some conditions on the solution space so that such a greedy algorithm works. If the conditions are satisfied by our problem, then the greedy algorithm works. Okay. I'll just give you abstract definition for now. In the next lecture, we'll see a couple of examples to illustrate them and so on. So let E be a finite set. Okay. So in the case of a graph, E is going to be set of all edges in the graph. So a matroid M over E is a pair E as well as calligraphic I, where I is a subset, collection of subsets. Okay, that is, I is a subset of the power set of E. Okay, with the following conditions. First condition is empty set should be 9. The second condition is it should be closed under subsets. That is, if A is in I, B is a subset of A, then B should also be 9. Third condition is a bit more intricate. So if you have two subsets in I, such that cardinality of the first subset is less than cardinality of B, then there should be an element in B which is not in A. By adding that element to A, I should be able to grow this set into an element in set in I. Okay. So this is called, let's call this as exchange. Yeah. So the exercise is, so let I be set of all matchings in G and for a given graph. Okay. So show that EI is not a matroid. Okay. I'll come with the S examples in the next lecture. Okay. So this is one exercise that you can think offline. Okay. I'll stop here.